Hi, today's video will be about acids. Many of our most important chemicals are acids. Um, the ammonium cation. Another important one is hydrofluoric acid. And the main subject of today's video will be acetic acid, which is the acid in vinegar, and whose chemical formula is CH3CO2H. And although there are lots of acids, they all act in very similar ways. And one way we're going to talk about today is the way acids act in water, and we'll use acetic acid as an example. So here's acetic acid, and we're going to look at its reaction with water. And what we're interested in is that to a certain extent, the acetic acid will lose one of their H's. They'll lose an H plus, so it loses an H plus, becomes CH3CO2 minus. And the water will gain the H plus, and I'll draw it over here, H3O plus. So to a certain extent, all acids to a certain extent dissociate. That's what this reaction in water. And chemists are very interested in the amount of dissociation. And it turns out that acid dissociation obeys, once the reaction is over for all acids, the same property. And that's it is based on the molarity, the concentrations, and you take the products. So the products of the reaction here are CH3CO2 minus, that's one product, and you multiply by the other product, its concentration, H3O plus, and you divide by the reactant. And we're not going to worry about water as a reactant. In acid dissociation water, we don't put it into this equation, so the only reactant is acetic acid itself. We look at its concentration. And it turns out that once a reaction is over, the ratio of these product concentrations over reactant concentrations is always equal to a constant, a different constant for each reaction. Here, we'll call it Ka. This is the acid this is the acid equilibrium constant, Ka, and for acetic acid, it's 1.6 times 10 to the minus 5 molar. So every acid has its Ka. And we want to know how much it dissociates, and it turns out that the best way to find out how much it dissociates is to use the ICE table. So I'll rewrite the reaction. CH3CO2H plus H2O going to CH3CO2 minus plus H3O plus. And we're going to set it up in the standard ICE format. ICE, and we have an initial concentration of the acetic acid, which I'm going to call MA, the initial amount of the acid, A. We're not interested in the water, so we'll skip that. And then we have initially no reacted acid, so we have 0 CH3CO2 minus and 0 H3O plus. And the reaction occurs, and we don't yet know how much the reaction occurs, and so we're just going to use an algebraic number. A certain amount of the acetic acid will react. We're going to say the amount that reacts is minus X. And X is some number we don't know, but whatever that number is, the same amount of products will be made. There will be plus X CH3CO2 minus made, and plus X H3O plus made. And if we add the I and the C lines, we get MA minus X. We're not worried about the water. X and X. And if we put it into our equilibrium expression, we now get that CH3 CO2 minus times H3O plus divided by the CH3 CO2H concentration. If we look at the E line, we see that is X times X divided by Ma minus X, and this whole thing is equal to the equilibrium constant. It equals Ka, and that is the kind of expression we get, typically written as X squared divided by Ma, whatever the initial amount of the acid was, minus X equals Ka, and X is how much dissociated. And it turns out that the amount that is dissociated depends on the relative sizes of Ka to Ma, and to understand how Ka and Ma interact with each other, we are going to need orders of magnitude. So I hope that was helpful, and that's it for today's video.